what I wanted to do is I wanted to take a few seconds here and I wanted to talk a little bit about internal curing in concrete. And some of you may be asking the question, what is internal curing? We're going to get into that. But before I get into all the details on this, I want to really mention that this is work that was sponsored by the Indiana Department of Transportation. Dr. Nantung is the research director for the INDOT. And helped out immensely, helping us get access to information. Also, this work is really a culmination of what a lot of different students have done. Overall, there have been about 20 different students. Three of the main players that I'll mention here, Javier Castro, who is now a professor in Chile, John Schlitter, who was a master's student who worked on this and as a licensed engineer, and Ryan Henkin-Sifkin, who's now working on the West Coast for a large ready-mix producer. These are really the three main guys who did a lot of the work that we're looking at here. So the first question really to get into is really what's internal curing all about. And I guess what I would tell you is if you want to zone out for the next 50 minutes or so, what I'm going to do is I'm going to give you the three main points of what internal curing is all about. So I'm going to give you the bullet. Essentially, it's to reduce the potential for cracking. Right? And we used to say reduce the potential for unwanted cracking. I'm not sure how much wanted cracking there is in concrete. So we're going to try to reduce the cracking potential. We're going to try to reduce the ingress of chloride ions. All right? We know we use a lot of chlorides to keep our roads free of ice. So by internal curing, we're going to be able to reduce how fast these chlorides get in and delay the rate of corrosion of our reinforcing steel. And then also we have a benefit of improved construction robustness. So all of a sudden now we're not as susceptible to slight changes in temperature. We're not as susceptible to improper curing technologies. We're not as susceptible to a dry, windy day when things are cast. So these are really the three things that internal curing is going to give us. Right? So this is the answer. And what I'm going to do is talk for the next 45 minutes or so about how we got to this point and how we manufacture internally cured concretes and show you some data that backs this information up. Right? Now when I say curing, most of us probably think about the same thing. We think about placing water on top of our concrete. So here we can see a concrete with a pretty low aggregate content, but this is just a conceptual drawing here. We've got some aggregates, which are these dark spots. We've got our matrix, which is this gray stuff. And when we apply conventional curing, what we're really looking at doing is typically, in the best case scenario, supplying external water, and that external water would sit up on top of the concrete. And about 15 or 20 years ago, we had some great debates with people in Canada on how this actually works when you start to look at high-performance concrete. One of the conclusions that was coming out is they were saying, really what we need to do is we need to just make sure we apply good water curing. And while good water curing is a very useful thing, in very high-performance concretes, we try to make a very dense matrix that keeps things from moving through the concrete. So just like if we make a very dense matrix that keeps chloride ions from moving through the concrete, we can actually restrict the amount of water penetration. And it turns out that if you use a reasonably low water-to-cement ratio concrete, you're only going to get several millimeters of water penetration, right, after about 18 to 24 hours. So if you think about this, let's assume the best case scenario where we're getting 10 millimeters or a half an inch of water penetration, we're really only curing the top surface of our concrete. And the middle portion of our concrete really isn't getting that additional water because we're making the system so dense. So really what we're trying to look at is there a way that we can make these mixes more uniformly cured? This becomes a big issue when we start to hear this with lower water to cement ratios, something called self-desiccation. Self-desiccation essentially means that the system is going to dry out without losing any water to the environment. And I'm going to go through what happens and why this self-desiccation occurs. And if anybody sits in the room and says, well, that's a Midwest thing, in Utah we don't have self-desiccation, I promise you, you have self-desiccation. Right? If your cement is hydrating, you have self-desiccation. The question is the level or the extent of self-desiccation that's happening, and that's really what we want to talk about. So a lot of people are running around talking about internal curing, right? But there's a little bit of confusion going on to what internal curing is. And while it may be hard to define, what I want to go through is really what we mean by internal curing, some of the technologies that are out there, and then I'm really going to focus in on the technology that I think is market ready. There are several places that are casting bridges right now using this technology. There's a lot of pavement that's been put down with this technology. This is something that's ready to be implemented and ready to improve the service life of our concrete structures. Now, We can go through a lot of different definitions on what internal curing is. You can think of internal curing very simply as controlling water movement and water release. All right, so other things that control water movement, all right, and water release, obviously our good friend the camel, all right, is going to release water at the right times. All right, here's my son who is very excited about controlled fluid movement, right? And the same technology that goes into controlling fluid movement here is one of the technologies that can be used for internal curing. Superabsorbent polymers. Superabsorbent polymers will draw water into them, right? And in the case of diapers, you don't want that water to be released. In the case of concrete, you want that water to be drawn in and you want it to be released at the appropriate time. All right, so there are really three technologies right now that are out there that are used for internal curing. One of them is superabsorbent polymers. Right? Today, right now in the US, there really isn't a superabsorbent polymer that's on the market that anyone's using. There are people who are using things like cellulose fibers. I'm struggling to see a lot of cellulose fibers being used. I haven't seen anyone using them commercially. And the third one, which is what we're going to spend the majority of our time talking about, is internal curing through the use of pre-wetted lightweight aggregates. All right? And we'll talk about the fact that this is a pretty good technology that we can actually use for internal curing. So to go back to our picture that we saw a little bit earlier, when we talk about curing in general, we've got our concrete, we've got external water being supplied. Right? This is external curing and we're pretty familiar with this. So what is it that we're looking for our superabsorbent polymers, our fiber, or our pre-wetted lightweight aggregates to do? Well, what we're really trying to ask them to do is we're going to replace some of these aggregate with this pre-wetted inclusion. So we're essentially going to have something that occupies space that is full of water, and during the mixing process, it simply occupies that space. After the system sets, it gives the water up to the concrete to promote hydration and to do what we need in the system. So what we can essentially see here is these green checkered areas are essentially our water-filled inclusions, or you could think about them as lightweight sands that have been pre-wetted where we're hiding water inside of that material. After setting, that water will be released and will essentially have an impact on the paste around the lightweight aggregates. Now, in a properly designed system, we want all of these affected areas to start to overlap. All right, so what we're actually going to do is do calculations to figure out how close we need to have the aggregates spaced so we can get this overlapping to occur, and I'll show you some of the types of calculations that we do. The basic premise, what it's all about for internal curing, pockets of water that are going to release, that you're going to have that water released at exactly the right time to hydrate the cement. Right? Same type of thing we're trying to do with external curing. The only difference is we're hiding the water inside of the concrete. All right, so what I want to do today is I want to go through a couple different features. I'm going to talk a little bit about the premise, right, why we need this and why it works the way that it does. I'm going to talk about our porous inclusions, our lightweight aggregate, and then we're going to start to get into some of the benefits. As time permits, I'm going to give you a little bit of an update on some field trials that have been done, and also to talk about how this fits into the larger problem of sustainability. All right, as our two guys over here fishing are noticing, it's all about controlling water distribution. It's all about getting the water at the right time, at the right place inside of the microstructure. That's really what we're talking about in this particular case. So let's start to talk a little bit about chemical shrinkage and setting. Now, you'll hear a lot of people who say this is a new technology. Right? Le Chatelier saw this in about 1870. Right? It's a new technology as far as the length of the Earth being in existence, but at about 140 years, we know that this is a technology that is out there. All right, Le Chatelier, all right, said that if I take 1 volume of cement and I put it together with 1 volume of water, I get what? 1 plus 1 equals? Exactly, 1.8. All right, so Le Chatelier said that when I start to react these two materials together, the reaction, the chemical reaction that goes on, results in a reacted product that's smaller than what I started out with. All right? This happens in every single cement. If you're not having a cement that undergoes chemical shrinkage, it's not reacting. This happens with every single cement. This happens in other materials as well. All right? There's a shrinkage that occurs in steels. Civil engineers never worry about it because it happens at 727 degrees Celsius. All right, it happens when it undergoes a phase change because the chemistry of the system starts to have volume of reacted products that are smaller. Crystal structure changes. Here, as the cement reacts with water, it undergoes a volumetric shrinkage that we're going to call chemical shrinkage. You can actually measure this chemical shrinkage as an indication of how much reaction has occurred, and it works out to be a very, very sophisticated measure of how to do this. Right, now what I want to do is I want to take a second and I want to think about what's happening and what's giving rise to this concept of self-desiccation in the system. So being an entirely pore artist, what I've drawn are spherical cement grains inside of this pore solution. And what we're going to do is monitor the volume change that occurs over time. Right? So as the cement particles start to react, you can see these rims reacting, or you can see some through solution products reacting. The system, as we just talked about, gets smaller. As the system reacts, chemical shrinkage occurs and the system gets smaller. Now, when the system is fluid, the system just keeps collapsing upon itself. At some point, these particles can no longer continue to collapse upon themselves. And we commonly refer to that time as setting. Right? At some point, the system ceases to be a fluid and starts to become a solid. So all of a sudden, as at one point, these particles begin to impinge upon one another, they can't continue to collapse, and the external volume change now starts to differ from the chemical shrinkage that's occurring. So what has to happen in these systems? Vapor-filled spaces need to start to form inside of our system. So these pockets start to open up, these vapor-filled pockets. Right? These pockets are going to give rise to that thing we called self-desiccation. Right? When we first started looking at this, we said we should be able to hear these pockets forming. And it turns out that we can use a technique called acoustic emission, and we can actually hear when these pockets start to form. They start to form right after setting. Right? So really the issue is here, these vapor-filled spaces are going to give rise to stresses developing in the fluid, they're going to give rise to shrinkage, and they're going to behave exactly the same way as if these vapor-filled spaces were created by water being lost to the environment due to drying. Right? So every system undergoes this. Right? The difference is it becomes crucial in lower water to cement ratio systems because these pockets are very small, the menisci are very small, and the stresses that have to develop in the fluid are very, very high. What are the consequences of this happening? So the consequences of self-desiccation, well, we're going to have increased autogenous shrinkage. This is shrinkage that occurs without moisture loss, shrinkage that occurs without a temperature change. So even if you take your concrete, you put visqueen on the top, you put your curing compounds on the top, you put your sealers on the top, it's still shrinking because of this chemical reaction. Right? The Japanese did some tests about 15 years ago. They took some of these blocks, they threw them underwater. The foundations cracked underwater because they couldn't get the water in from the outside and it was undergoing this chemical shrinkage. Right? So you're going to get increased autogenous shrinkage and increased cracking potential. In addition, what we start to see as these vapor-filled spaces start to form, we start to reduce the relative humidity inside of our concrete. We actually reduce the pore pressure inside of our concrete. We make the water less chemically active in the system, which means that it's not able to hydrate as much of the cement. Here you can see a pretty old chart that comes out of some work done at PCA in the 1940s that says essentially if you have 100% relative humidity, you've got a lot of free water, you get a lot of chemical reaction going on. However, as the humidity starts to drop, you start to drop how much of that cement can be reacting. So another potential cause or consequence of self-desiccation is you're really going to limit the hydration reaction, which limits strength development and gives you higher transport because you can't fully disconnect all the pore network inside of the system. Now I know there's a bunch of people sitting in here and saying, whoa, wait a second. This is some radically wild stuff. I've poured concrete for 30 years. I have never seen these vapor-filled spaces form. I don't know what this guy had with his chocolate cake at lunch, but this stuff is way out there. I'm going to ask you a question about just what we see every day in concrete. Now, I grew up, my father's a contractor, and I understood that at some point, it's exactly the right time to finish a concrete slab. Right? So let's assume this is our concrete. We know that bleed water comes to the surface. Actually, the rest of the concrete sinks down around, the bleed water stays behind, but let's not worry about some of those details. Finishers know the exact time to get on there and finish the surface is when? Once this bleed water disappears, I was always taught as a kid growing up you had time to smoke just one cigarette and get back out there and start finishing off the surface. Right? Why is this bleed water going away? Well, as your concrete sets, those vapor-filled spaces would rather pull water in from the outside than to leave that water sitting on the surface. So at the time of setting, that bleed water, that sheen goes away because the capillary stresses pull that water back into the system. Right? So this happens every single day, and it just so happens it happens at the time of set for the same mechanisms that I was talking about before. Now, we want to talk about ways that we can hide water inside of this system. And what we really worry about with our water to cement ratio is we worry about keeping the water to cement ratio low until the time of set. Because at that point, we want to lock the microstructure in place. We want to lock that porosity in place. All right? The whole key, the whole premise to which this works on, all right, is again my horrendous cartoon skills over here, but we have different size pores inside of our concrete. We've got big pores, we're going to call them capillary pores. We've got small pores that we can call gel pores. All right? The basic premise of all of physics is big pores empty first. It's lower energy for the big pores to empty. All right? The bigger pores, all right, are going to empty first. What we're doing with internal curing is we're hiding water inside of lightweight aggregate that's a slightly bigger pore than we have inside of our paste. So preferentially, at the time of setting, these vapor-filled spaces want to form inside of our matrix, but instead of forming, they're going to suck the water out of the lightweight aggregate. Now this is pretty nifty. All right, if you think about this, a lot of people are talking about smart materials that do exactly what you want at the right time. What we really wanted, if we wanted to design a material to do internal curing, we want it to hold its water until the system sets, and then after setting, we want it to give its water to the matrix to keep this full so we can hydrate all the cement. This is exactly what the lightweight aggregate is doing. Right? This is pretty impressive, I think, from what we're looking at. So again, to get into this idea, this is my idealized lightweight aggregate. It's orange. All right? These are the cement particles. As the system starts to hydrate, these vapor-filled spaces would start to form. Instead of forming those vapor-filled spaces, we suck the water out of the lightweight aggregates. We keep the matrix full. We keep the cement paste hydrating. We keep the stresses low inside of the overall system. Right? Now, the next thing that's always asked is, well, what lightweight aggregates can you do this with? How many do you need? What size is the right size to use? Right, we're going to start to try to talk about some of those. Right, the first thing I'm going to say is we've tested all of the lightweight aggregates in the Americas. North America, Central America, and what I will tell you is they can all be used for internal curing. All right? Generally, you want to use the local materials because they're going to be the ones that are the most economic for you to get because of shipping and other things like that. So I will tell you that local materials to Salt Lake can be used for internal curing. Right? Now the next question is, well, what size lightweight aggregate do you want to use? This is a computer program that was developed at NIST, and essentially here you can think about this, these red particles are normal conventional aggregates. The space in between the particles is your cement paste, and these yellow particles are your lightweight aggregate. The only difference between the top picture and the bottom picture is the size of the lightweight aggregate. They have exactly the same volume of lightweight aggregate. This is a coarse lightweight aggregate up here. This is a fine lightweight aggregate down here. The whole goal to making this work is you want to have these lightweight aggregates distributed throughout the system so that all of this paste is very, very close to an aggregate. Because remember, water can't travel that far. So typically, water can only travel about 2 millimeters. The 2 millimeters is shown here as aqua. And what you can see is from this big coarse aggregate, we can essentially assume the water gets out into this range. But there's a whole bunch of the matrix that didn't get that water that came from the lightweight aggregate. If you use the sand, all right, that water gets distributed. So the question was, why does this happen? All right, this matrix becomes very, very dense. So if you've got a 0.3 water to cement ratio, you can't get this water to travel after about 18 to 24 hours. And I'm not going to go into it here, but we've done a lot of work with a technique called neutron tomography. It's like a CAT scan that instead of using X-rays uses neutrons. We can essentially find out that the water only moves about 3 to 4 millimeters in some of these high-performance concretes. So the real goal is to not necessarily use a particular volume of aggregate, but to make sure that you're using a volume of aggregate that's well distributed throughout the system, replacing a portion of the sand, all right, in doing this. Now, as I mentioned before, there are about 18 different sources of aggregate to be used. They have very different absorptions. One that's probably typical to Utah is right around in here, where you've got about 17 or 18% absorption at 24 hours. They can all be used to internally cure your concrete. The only difference is how much lightweight aggregate you're going to use. And in general, there's an equation, and if anybody wants to see the derivation of the equation afterwards, I'll be happy to discuss it at great length with you. But I will tell you that it boils down to a very simple rule of thumb. For every 100 pounds of cement, you want to hide 7 pounds of water in your aggregate. For the local aggregates, that's about 225, 250 pounds of sand being replaced in the system with lightweight aggregate. Okay? Now, I've talked a little bit about water absorption in your aggregates, 16, 18%. But really the key issue is not necessarily water absorption. It's how easy is that water released back to the system. In addition to measuring absorption, we've actually measured the desorption of the different aggregates. And what I would point out here again, this happens to be an aggregate that is not a shale, slate, or clay. This is a non-lightweight aggregate, but it's a desorption behavior. What we want is we want to know how much of this aggregate moisture can be lost at relative high humidities, 95, 96%. The thing that's very interesting about this is your lightweight aggregates will drop about 90 to 95% of their water at these high humidities. So what does this mean? This means that they have pore sizes that are bigger than what we see inside the paste, so they readily give up their water when it's needed. This is exactly how you would engineer a system to get the optimal type of performance that you would want. So you're getting the most efficiency. Does that mean you couldn't use this aggregate to get internal curing? No, you could use it. You would just need to use more of it than you would see with a conventional lightweight aggregate. All right, so what are some of the benefits? All right, obviously hydration is a key issue. If you do not keep the system hydrating, all right, you've got some big problems in how that system is going to perform over its life. All right, now, these pictures here are essentially two different types of images. This is a look at cement paste on the nanoscale, where essentially you're looking through a microscope that essentially interacts with the paste by dragging a very expensive record player needle across the top of the surface. And what you can see is we get a very, very dense system when we've got a lot of water inside of there to hydrate the overall system. This is the edge of one of these lightweight sand particles, and what you can start to see in here is we've essentially got these dark spots, which are porosity. But as water leaves these big pores in the lightweight aggregate, it fills in this matrix and makes a very, very dense matrix. Particularly, it makes it very dense at this interfacial zone. Right? This is not what we see in most normal weight aggregates. Most normal weight aggregates, we see a porous region at the edge of that aggregate. That porous region essentially allows things to transport through it much more quickly. With internal curing, lightweight aggregate, we see a very dense region here, but we also see very dense regions as we move away from the aggregate, which means it's going to be harder for things to move through the system. Harder for chloride ions to move through the system. Harder for sulfate ions to move through the system. Harder for small children and dogs to move through the system. All right, we're densifying the system, all right, to try to keep things from flowing through the system. Now, what is one of the biggest benefits of internal curing? Well, it's reducing that effect of self-desiccation, reducing the pressure that's developed inside the fluid. The second biggest benefit that you see with internal curing is shown right here. This is the amount of heat that's been released by a cement paste with different water to cement ratios after 3 days. Right? These dots are internally cured mix. These blue dots are essentially a conventional concrete. And what you can see here is more heat is being released when you've got internal curing. And I can already see a couple eyes going, big whoop, more heat was released. How does that help us? Well, heat release is a direct measure of how much cement has reacted. So what we're essentially saying is, at 3 days, we've reacted more cement in the internally cured system. Why are we reacting more cement? Because we've got that additional water there. We're keeping the humidity higher. Right? We're using more of the cement that's inside of the system. At 7 days, this difference grows. At 21 days, this difference grows. So the benefits of internal curing are you're going to get more reaction inside of the system. This is important for Portland cement. It becomes even more important when you've got supplementary materials. You're using slags, you're using fly ash, you're using silica fume. Even more and more important. Right? Again, we saw this before. Keeping the humidity high allows more reaction to take place inside of the system. All right, so here's our conventional mortars. Our plain system may drop the relative humidity down around 85% at the end of the first week. 85%, you're down in this range here. Our internally cured mixture, we're up around 95%. We're way up in here. More reaction going on in the system because we're supplying internal curing water. Right? When we get more internal curing water, we keep the system moist, we keep the system reacting, we keep hydrating the cement, which means we're going to have lower porosity in the overall system. Right? One of the most important things that internal curing does, right, is something that Nancy Reagan advocated years and years ago. Say no to crack. All right? Cracks are a problem in bridge decks because they allow water, chloride ions, direct access to our reinforcing steel. Right? So a few years ago it became really obvious that our conventional measures for measuring shrinkage really start to fail when we talk about high performance concretes. Because our conventional tests essentially say wait 24 hours and then start measuring shrinkage. How did our concrete know that it should start shrinking at 24 hours? As we saw earlier, shrinkage really starts from the time the water and cement come in contact with each other and becomes a real big problem once the system starts to set. So what we've essentially done here is we've essentially been working with a test procedure that's essentially like a big crinkle cut French fry. This is an accordion type of tube which has very high stiffness in the radial direction, almost no stiffness in the longitudinal direction, so you can measure length change from the time the concrete is fluid. You can zero this at the time of set and you can start to measure these length changes very early on. Right? We can also measure these in sealed systems and do other types of things to measure the overall length change. Now, there's a lot of data on this graph, and I will promise if anybody wants to see data, I will be more than happy to send 3 or 4 of the most voluminous theses I've ever seen in my life, and I will be happy to talk you through any questions you have on these. I don't want to get hung up on all of the different numbers and what everything means. Here we've essentially got free shrinkage. The blue is a conventional mix that we got about 400 microstrain of shrinkage after 28 days if the system is completely sealed. So you've applied your curing compounds perfectly, you've got plastic sheet on top of it, you've got 400 microstrain of shrinkage after 28 days. Okay. With internal curing, we get a slight expansion because of the release of water. Right? We know that it swells. And then what we'll see is if we put enough lightweight aggregate in the system, we essentially don't have any of this shrinkage. All right, so what does that mean when we start to look at this? Well, here's where we start to look at a slightly different test, and I'm going to stretch our imaginations a little bit. This is a test technique that's called the ring test. All right? Obviously, you look at this and you say, aptly named, it looks like a ring. All right? What is the ring all about? Well, we've got a steel ring on the inside, and that steel ring has strain gauges on it. We place concrete around that ring, and if the concrete wants to shrink and get smaller, the steel prevents that from happening. So the concrete says, I want to shrink and get smaller. The steel says, no, I'm going to restrain you, I'm not going to let you move where you want to move, and it pushes back. This is a lot like what girders do to a bridge deck. The bridge deck says, I want to shrink and get smaller. The girder says, it's not going to happen. Stresses build up inside of the concrete. And if the stresses build up to a high enough level, you can get cracking. Now, we may look at this and we may say, well, this doesn't look anything like a bridge deck. Why would somebody want to use this? Right? Well, we've all been to a wedding and someone gets up, right, and we hear them talk about the ring. The ring is like a circle and love has no end. Right? There's no end effects. Right? We don't have to worry about gripping the end of the sample. All right? So essentially, this becomes a very easy test to run. Dump a bunch of concrete around a piece of steel, step back for 28 days and see what happens. Right? We can actually do that, and we can start to look at the strains that develop inside of the system. And I will mention that there are equations out there that directly relate the strain that's measured inside of the ring with the stresses that develop inside of the concrete. Our blue, again, is our plain system. Sealed, after 6 days, the system cracks. This big jump here is the release of stress in the system, which occurs because of a crack. As we add more and more lightweight aggregate, we see almost no stress developing in the system. Right? This means that we have more capacity inside of the system, right, for loading, for thermal changes, for other things happening before the system would start to crack. And if we start to look at this, we can essentially see a plot of the lightweight aggregate along the x-axis versus the age of cracking. And what we can see is once we get to a critical amount of lightweight aggregate, this line starts to approach an asymptote, which essentially means that these mixes don't crack. If we have a system that undergoes both the sealed shrinkage and a drying shrinkage, we can see we need a little bit more lightweight aggregate, but again, we can get to a system that's not going to crack. Right? We would have designed this mix just for self-desiccation to be at 23% lightweight aggregate. Right? If we do that, we can keep the system from cracking. Right? We've seen this over and over again when we do these different types of trials. Right? Now we said, well, this is actually, believe it or not, this becomes a problem. Because how do we start to test concretes that don't crack in the lab? So we built this thing that looks a little bit like a still. All right? So what we've essentially done is we've said, well, there's some issues with the conventional ring test. First of all, expansions that occur we don't necessarily capture. So we have a ring on the inside, a ring on the outside. Right? In addition, we make these rings out of a special type of steel that has almost a zero coefficient of thermal expansion. So if we change the temperature, the rings don't start moving around. And we use this chilled water loop to control the temperature in the system. So what we're going to do now is we're going to essentially say over a time period, we are going to measure the stresses that develop in the system, and we're going to monitor and then control the temperature. So what I want to do is I want to focus over here on a pretty typical bridge deck. And what we can see here is that we would see stresses starting to develop. And at some point, these stresses really start to take off. These stresses start to take off because at 72 hours, we started to drop the temperature. Right? It took 10 degrees Celsius temperature swing to get cracking in our conventional mix. Now you may say 10 degrees Celsius, that's about 20 degrees Fahrenheit. Can it change 20 degrees Fahrenheit from day to night in Utah? I think so. At 3 days, this bridge deck is going to crack. Your internally cured mix, right, we do the exact same thing. It takes 30-degree temperature swing, actually 27.1, to cause cracking. So we've built in a lot more robustness into this system. We can undergo a much more substantial temperature swing before the system would crack. This helps us to get that concrete through this sensitive time, that first week, that second week after casting, to make sure we're going to have a concrete that remains uncracked. So what we can see is we get a little bit of a benefit here where we start to change it from a 10-degree swing to a 27-degree swing. We also notice, though, that there's a much slower stress development in the system. And this is due, one, to the fact that there's more moisture in the system, and that changes the coefficient of thermal expansion. In addition, we change the stiffness of the concrete because we now have a system that's a little bit less stiff. And by having a system that's a little bit less stiff, we have benefits in that we're not building up as many stresses inside of the overall system. Now, you can go through and you can do this at many different ages, not just 72 hours. All right, and you can see that we dramatically increase the reserve capacity when we start looking at internal curing. This means we can have a greater temperature swing, greater loads applied to the system before we would start seeing cracking. Now, in addition to doing these small rings, we've said, well, let's see if we can do this on larger sections. There's a room that's set up at Purdue where we essentially have the ability to control temperature, moisture, and wind speed. We can do this on samples that are up to 35 feet long. Right? In this case, we're actually doing this on bridge deck sections, all right, where they're essentially 3 feet wide and about 15 to 16 feet long. And what we see is that at 50% humidity, all right, a 30-mile-an-hour wind, for 12 days, we see a 0.3 system started to crack. With internal curing, we had to go out to 43 days to get this system to crack. If you've got a bridge deck that's exposed to 50% humidity and 30-mile-an-hour winds for 43 days with nobody doing anything to protect it, right? You're going to have a system that's pretty durable here. Right? Now, we heard a lot about how fast do we need to start repairing some of these bridges. Right? In addition to worrying just about early cracking, we're worried about long-term durability. Right? So while Noisy was worried initially about that moisture, all right, and keeping it away from his skin, now all of a sudden he's worried about, are we going to have to replace this bridge? There should be no bridge decks we replace in my lifetime. The question is, are we going to be replacing these bridge decks in Noisy's lifetime here? All right? So what I want to do is talk a little bit about some of the fluid transport mechanisms that are happening inside of the system. Very simple test that can be done to evaluate the performance of concrete. Place a mortar inside of a fluid and measure how fast that fluid gets sucked up into the system. Right? We can do that and we can come up with a plot where we can show either the absorbed water, all right, of the system, or we can show the rate of absorption versus the water to cement ratio. Not surprising, higher water to cement ratios have more porosity in the system, they suck up more water. Doesn't shock anybody in this room, I'm sure. What is really interesting is let's look at this blue point. This blue point is our internally cured concrete. So it's cast at the same water to cement ratio this one is, but it performs like a lower water to cement ratio. So it's cast at a 0.3 water to cement ratio, but it behaves like a 0.23 water to cement ratio. You may say, well, wait a second, how did this all happen? Well, remember, we're hydrating more of the system. And if we measure the porosity, what we see is everything falls along a single line. So the benefit that we've got with internal curing is we've disconnected those porous regions at the aggregate interface and we've densified the structure. We've got less porosity in the system because we've hydrated more of the cement. Same thing happens with electrical conductivity. Electrical conductivity, you may say, well, we don't use electrical conductivity, we have other measures here. This is essentially the inverse of the rapid chloride permeability test. All right, so the 1202 or the RCPT test, right? Again, a 0.3 behaving like a 0.23 because we've got increased hydration happening in the overall system. All right? Now, a lot of people are going to say, well, this only works if I get to a 0.2 water to cement ratio concrete, and we don't do that. We pour at a 0.36 or a 0.4. What I'm going to point out here is maybe early on, 1 day, 3 days, 7 days, you're not going to see a huge benefit because the system still has a lot of water to continue hydration. After a year, though, we can look here at the red dots, which are a 0.3 system, and a 0.42 system, which are these blue triangles, and we see that this helps both systems. This supplies additional water, and actually what we've seen is this is more beneficial for mixtures with a 0.36, 0.39, 0.42 water to cement ratio when we start to talk about long-term transport properties. Same type of thing when we start to see chloride ingress, internal curing, we see benefits. Right? Another benefit, reduced plastic shrinkage cracking. We have additional water. That additional water can essentially account for any evaporation that's happening very early on. Now, some of the things that I will mention here, this is some field testing that's been done. There are about 12 bridge decks that have been done in New York State. We've walked these. With the exception of one deck that I think has some structural vibration issues, they all have at most one crack that we saw in the negative moment region. Right? And it's a very small crack because there were 16 of us standing out there, all right, with one guy on his hands and knees looking for this crack. This was a study that we had done in Indiana where I said I want to have two bridges that are next to each other because I want to cast a conventional mix and an internally cured mix back to back, and we want to evaluate these performance. So here's the internally cured one that's being cast. I will mention that early on we said we have to cast this with a bucket because we're worried about pumping it. That's no longer a concern. We're not worried at all about pumping it if the aggregates are properly pre-wetted. And then we went back a year later and we looked at some of these decks. This is a picture off of the conventional INDOT approved mix design. It has two nice cracks that go right through the bridge. The internally cured one shows no cracks. Now, there are a lot of reasons that cracking can occur, but these are almost identical bridges, cast one day apart, the same construction crew, the same time, with the same materials. The only difference is one had internal curing, the other one didn't. In addition to not having cracks, the internally cured one had about a 10% lower strength at one day, but it had 30% increase in strength, all right, as we went on. By about 3 to 5 days, they had equivalent strengths. The internally cured concrete had 10% lower permeability at 1 month and 40% lower permeability at 3 months. Lower permeability translates into it's going to take your chloride ions longer to get to the reinforcing steel. It's going to delay the corrosion of that reinforcing steel. We've been doing some studies where we're trying to measure corrosion rates. It was real easy to do for the restrained conventional decks. They started to corrode very quickly because they had cracks in them. The internally cured ones, 2 years later, we have no corrosion data, all right, because they haven't started to corrode. You've got lower permeability, and you've prevented cracking inside of the overall system. So I want to give a brief summary, and then I'm going to hit some high points on some of the things that we're working on now to extend this a little bit. Internal curing, localized pockets of curing water that are going to do exactly the same thing we did with external curing, but they're going to do it inside of the concrete. Setting causes these vapor-filled spaces to form. What we want to do is fill them with water from the lightweight aggregate. In addition to reducing shrinkage and cracking, we can improve our transport properties. We can increase durability because we've reduced the interfacial transition zones and we've increased the hydration that happens in the system. And we also see benefits in terms of thermal change and plastic shrinkage cracking. In addition, though, this has some other big benefits. We can use our cement more efficiently because all of a sudden now we can hydrate more of that cement. So as we grow to greener and greener cements, Portland limestone cements, we start to use more supplemental materials, we've got some real big benefits in here. So what I want to do is I want to mention a project that we've been working on recently for the Federal Highway Administration, where we've essentially said, let's take a conventional mix and let's find out what happens if we reduce the water to cement ratio. We reduce the water to cement ratio, we increase the compressive strength, nothing real magical. But what we're really doing is we're saying we want to have our conventional mix, which is this blue line, and we want to take 60% of the clinker out of that concrete. So we're going to take 60% of our conventional cement out and we're going to replace it with a fly ash. And what we've been able to see is at about 7 days we have almost equivalent strength. All right? And if we do it with 40%, we have an equivalent strength at 1 day. 40% less CO2. 60% less CO2 if we have equivalent 7-day strengths. Now you may say, well, what is all that doing? We're essentially lowering the water to cement ratio, but then replacing a lot of the cement, so we're maintaining these similar strengths at early ages. We use internal curing, and that helps us to bump up the strength because we're getting more hydration of that fly ash, more hydration of that cement in the overall system. Now, in addition to just looking at compressive strength, we've looked at some other factors here. And maybe it's coming up. It's one of the world's slowest graphs. Come on, little graph. All right, but what I'll start to do here is I'll start to say this blue line is our conventional bridge deck mix. If we lower the water to cement ratio, we drop it to a 0.3, we see the stresses go way up in the restrained shrinkage test. If we now start to replace 40% or 60% fly ash, we can see our 60% fly ash system cracks. Our 40% fly ash system has a very interesting behavior here. The stress continues to go up and up and up over time. This is because fly ash has more chemical shrinkage and it takes place longer because it's hydrating for a longer period of time. If we take these mixes and we use internal curing, we drop those stresses right back down to what we saw in a 0.42 water to cement ratio. So really what we're looking at sustainability here is we're saying we can replace 60% of the cement, get rid of 60% of the CO2 using fly ash combined with internal curing. In addition to that, we get rapid chloride permeability numbers that are about 10 times lower than what we see in a conventional, the conventional mix design. So we think that there's some huge benefits here because we're going to enable greener concretes to be used, gives us reserve capacity, and really reduces fluid transport. And with that, I will see if there are any questions. And this is a really tricky thing because I've now asked for questions, but I can't see any hands because I'm staring into the sun. So question?
What's the mixed design approach? How much lightweight aggregate are you suggesting to add, or is that based on the absorption of the specific lightweight aggregate you're using? Is there circles of thumb?
Yeah, so the question really is, how do you determine how much lightweight aggregate to use? There's an actual equation to use where we essentially say there's a supply and demand. We say the mass of the lightweight aggregate times the porosity of the lightweight aggregate times how saturated it is sort of the supply of water that's there. The demand is how much cement you have, how much chemical shrinkage you have, and how much reaction you have. All those are numbers that we know, and it turns out that you want about 7 pounds of internal curing water for every 100 pounds of cement. In a typical mix like we'd be talking about here, we're replacing about 225, we're putting in about 225 pounds of lightweight aggregate to replace the sand. So we're replacing about 25 to 30% of the sand in a conventional mix.
Does that hold true for a lot of the different sources?
Yeah, so essentially the one thing that I think is really interesting about this, and I was as surprised as anyone else when we started to see this, you can apply this equation that I just mentioned to every single source of lightweight aggregate that's out there that's an expanded shale, clay, or slate. And they all work exactly the same. We've measured 18, we've tried it with about 7, but the same equation works. And I mean, if you've got questions, I'm more than happy to work through a mixed design with somebody, but it's really a pretty straightforward approach. All you're doing is replacing the amount of sand with enough lightweight aggregate to give you that 7 pounds of water for every 100 pounds of cement. Okay. And in most regions, I have to be careful because I'm in a state that this is not the case because we have aggregates with different absorption capacities. But in most places, you have a relatively small number of absorption capacities, so the replacement becomes pretty easy to calculate. All right.
Is it cement or cementitious?
It's cementitious, and what I would point out there is, while we know that there's a chemical shrinkage that occurs with the cement, it's higher for fly ash. It's about twice as high for fly ash. Slag, it's about 4 times higher when you get to silica fume. All right, so there's a little bit of an adjustment that goes into that, but you essentially are replacing it on the total cementitious. And that equation I mentioned, we have all those corrections, but I didn't want to get bogged down on which number you put into the equation, but we've got a report I can send you, and I'm more than happy to work through a mixed design if that's, all right, if that's the question. Other questions? Question here?
The cost percent, I know cubic yard wise, this might be hard to say, but as a percent of cost, how much more might this mix cost?
Yeah. Well, the first thing I'll mention, oh, that's even better. What I'll say is, as a university person, I never get involved in costs. All right, but I will answer your question on what we've done in polling on these different construction projects. We have seen costs anywhere from $0 a yard to $12 a yard more with the internal curing. All right, and there's a question of how is $0, because you're replacing sand, and it has to deal with how close the aggregates are, where you're at. But you're looking at a $0 to $12 per cubic yard sort of cost addition, all right, just on the concrete. But I also will point out something, that there's studies that we've been doing, there's studies that are coming out of Canada that are suggesting that you double the service life of your concrete when you do this. So if you think about this, $10 a cubic yard more, $12 a cubic yard more compared to twice as long service life, to me it's a pretty easy calculation. When I mentioned this, I was told by someone we'd have to be stupid not to do that. I didn't want to agree on the part that I would insult someone, but to me it seems to make a lot of economic sense. Okay.
Did you use any air and train concrete when you did this?
Yeah, so there's actually a pretty good discussion. The question was related to are we using air and trained concretes? All the field ones are air and trained. And I had a lot of questions because I'm a university guy and I get nervous about everything. And then when I went and talked with the people in New York, they said they use their pressure meter. They don't have a problem with it at all because their aggregates, we're using a relatively small amount. They use that to measure their air contents. We've done it in the field. We've had no problem with the air contents. I will also point out that we've made concretes in the lab and have had no problems with freeze thaw, mainly because we help to reduce the degree of saturation of the system. So in a conventional system, you may have about 70 or 80% saturation. We see it drop down to 50 or 60%. It becomes harder for that water to get back in the system. I think more research needs to be done before we start shifting to that, but I think that's definitely a direction we can go. Right now, I'd keep the air in the system. Okay.
For a concrete pavement, would you change your joint spacing? You would still have joints?
Yeah, so the question is, what do you do when you start to get to a concrete pavement? I mean, one of the benefits that I didn't mention here is you start to see a reduction in the curling of the system because you got water more uniformly distributed throughout the system. Can you start to change your joint spacings? Intuitively, I would say yes, but we haven't done the calculations. And before we do calculations, I would hate to say, yeah, sure, go wild, double your joint spacings. But we know that we substantially reduce the curling in those systems. Other questions? Concerns? A joke? No? Okay. Thank you.